Okay, then let's look at a real application. So the idea now is that, okay, so we can classify. We've classified some flowers, which is maybe not so exciting. So now let's classify some handwritten digits and see if we can. If you give me a handwritten digit, if you can train a machine that can recognize what that digit is, right? So that's a classification problem with 10 outcomes from 0 to 9. And now that seems a lot more complicated, right? Because there's maybe not so many. Ideally, we don't really want to manually measure. If a new digit comes in, we don't want to manually measure what is the distance between if there's a circle in there or not, right? So we should just work without us having to measure or extract certain features manually. So this is also known as optical character recognition, OCR, and it's a very famous problem, and there's a huge research community still working on improving OCR. So again, we are lucky enough that sklearn comes with a data set with some digits preloaded. So it's called datasets.loadDigits. And then we can see it contains there's this digits.images, which is a dataset of containing all the images of some handwritten digits. And then if you look at the shape, it's got 1,797 samples. So these are the number of data sets that we work with. And then for each data set, we have 8 by 8 matrix, which means that we have an 8 by 8 picture containing the pixels of that digit. So we can look at them. So I just loop over some of these digits and actually plot them with the correct label. And this is how it looks like. So every single picture here is one example that we want to use to train our machine, and then the green number is the correct outcome for the label. Okay. So we have a bunch of we have in total 1,800 of these examples. And so you can see that this is fairly coarse resolution, first of all. And secondly, it's quite, even for humans, it's quite difficult to see what the outcome is if you don't know the answer. So if you look at this example up here, right, that's supposed to be 7, but if I looked at that, it could have just as been a strange 3, for example. So it's going to be quite challenging to, well, the first intuition is that might be quite a challenging task to train a machine. So obviously the computer doesn't work with images directly, but instead we have to represent the image somehow as an array. And the way that works is that each image is represented as an 8 by 8 pixel array containing the amount of grayscale in that image. So essentially, if it's 0, so here you have the example of one specific image, and each row corresponds to one row in the image. So it's an 8 by 8 image. And if you have a 0 value, then the background is then it's white. And if it's, I guess, 16, then it's going to be black. Okay. So this is the data that we work with. And because in NumPy we don't actually work with, so here the data is in 2-dimensional array itself. But NumPy expects our data samples to be just one-dimensional, a long one-dimensional array. So what we simply do is that we flatten out these images to one long array. So essentially, the actual data that we then work with is number of samples times 64, which is just 8 times 8. And and each vector just contains all the data points of that edge. So we flattened our images to arrays. And then the target labels. So that's simple. So I mean, the labels are just from 0 to 9, and that's exactly what we can work with also in classification. So we just keep the numbering 0 to 9. So in summary, we have 1,797 samples, and we have 64 features. So in this case, we decided to just use the pixel grayscale, the grayscale of each individual pixel in our image as a feature. We could have chosen also other things, but that's kind of the simplest way to do things. So we have 64 features in that case. So let's try to classify that. So we do it the right way. So the first thing that we do is we split up our data set into training and testing data set. So I again use this train test split method. And then I get 1,347 training data sets and 450 test data sets that we can work with. All right. And then we use our what we've learned just previously. So I decided to use a logistic regression method here. So I just initialize the logistic regression. I just choose a special penalty metric here. But then essentially I use the fit method and pass in both the training data and then the training labels, this Y train. And then I can use the prediction function to predict all the test data that we have. So then we have these Y prediction. And then we can work out what the accuracy score is. And you can see it's fairly high. It's almost 95%, which means that so the way you should read this now is that we used 1,347 data points to train the machine, and then out of the 450 test sets, we got the right digit in 95% of the cases. Okay? So for such a simple, for just a few lines of code, that's a fairly respectable result, I would say. Now, one disadvantage of just looking at this number is that it doesn't tell us what went wrong with the last 5%, right? So in order to improve things, we want to understand which part isn't working so that we can start addressing that. And so for that, there's something called the confusion matrix. And it's essentially a matrix that has number of it's the number of classifications both on the x and the y direction. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 on the x-axis, and then 0, 1, 4, 5, 6, 7, 8, 9 on the y-axis. And on the x-axis, you have the true classes are here on the x-axis, and on the y-axis you have the predicted classes. And so essentially what it tells you here is that we had 42 test samples that contain a 0. This is this number here. And in 42% in 42 cases we got the right prediction because there's zeros here everywhere. If we had made a wrong prediction, then this number would be lower and we would have non-zeros down here. So essentially what it tells you is that with the number 0, our algorithm got never confused. Now let's look at one where we actually got confused. So here we had 45 ones. No, we had in total 49 ones. But unfortunately, we only detected 45 times that it is a 1. And in two cases, we thought it is a 0, 1, 2, 3, 4. In two cases, we thought it's a 4. and then in 2 more cases we thought it's an 8. So this is how you're supposed to read this. So you can kind of figure out now in which cases did the algorithm do something wrong. So this is the so-called confusion matrix. And then we can also plot this in a nicer way. So this is essentially the same thing now plotted with a heat map. So the more blue it is, the higher the numbers are. And then you can nicely see, okay, where are there? Where is there something on the off diagonal? So here it seems like we seem to have confused 8 and 9s sometimes. Yeah. And so then also what is quite nice, what is quite useful is that you print the test, you print the entire test data, and you print both, you show the image, and then you show the prediction, and you mark the prediction as green when it was correct, and red when it was incorrect. So here you can see when things were correct for the first times, and then here our prediction was an 8, but actually if you look at it, it's more 4. Right? And then here we predicted a 1, but it is actually, well, I don't know what that is. It's probably also 4. And then here we predicted an 8, but it's actually 6. Yeah. So now if you start looking at these numbers, so clearly we aren't always correct. But now, so now we have 2 options, right? So if you wanted to, so the first observation is that even with kind of very simple methods, we haven't optimized anything, right? And we have a 95% accuracy, so that's already really good. But now if we wanted to improve that, we could essentially, we could try and play with the algorithms, try some different algorithms, maybe try k-nearest neighbors and all the different options that we have in there. But we could also try and extract some more features, right? So maybe this pixel-wise feature selection wasn't actually so clever, right? Maybe we should have developed an algorithm that can detect circles in an image and then use that also as a feature in our training step. So in general, if you do machine learning, this is actually where most of the time goes in. It's getting the data and actually preparing the data in such a format that they're all roughly the same, right? They're all 8 by 8 pixel. They're all centered around the digit that you're working with, and then deciding on which features do you actually want to use. The more work you put into the feature, the better the outcome is of your predictions. And then, of course, playing around with the algorithms and finding the optimal settings. Okay. Any questions regarding classification? No? So now you can. I always wanted to build a classifier for the Norwegian sops. What is that? What is sop in English? Mushrooms, yeah. Because I would like to go mushroom picking, but I don't trust myself. Yeah, it's a bit risky. Huh? So there you want to have a classifier that is absolutely certain before you start picking it. So you should really have a green light. But I don't know if there's good data out there. So maybe and I don't know what good features are. But yeah. Okay, but you can think of your own. You can think of your own classification problem that you would like to implement. Okay, so then the next part is regression. So regression is remembered. So in classification, the outcomes was always a finite number. So we could represent this as integers. So regression is essentially the same, except that we now work with floating point values. So whenever you have a problem where you can't just put a number to it, but maybe have a continuous outcome, then you want to do a regression. But overall, the idea is still the same, right? So we have some data and with known outcome, and now we want to build a model that can predict us what the outcome is for new data. And so one thing I also wanted to mention So in general, when you do these kind of predictions, predictions always work relatively well if you do so-called interpolation, which means that when you're predicting points where you have that are not outside your data range. Right? So in this case here, here we have data from going from -20 to 60, as long as we do predictions that are kind of in the range between -20 and 60, then the predictions are typically relatively good. But if you're trying to do predictions that are outside the data range that we have, then things become a lot more complicated. And then typically you can't really trust your model, or you need really complicated models. And so that's both true for classification and for regression. And so that's why it's relatively easy to say, if you know the temperature yesterday and today, I can, with relatively good accuracy, tell you what the temperature was tonight. But if I know the temperature from yesterday and today, and you ask me what is the temperature tomorrow going to be, or in 1 week going to be, right? So that's a completely different question. And the biggest supercomputers are working on that question. Right? So there's a huge difference between, which is so-called interpolating, where you're trying to find predictions inside where you have data, right, or you have data in your neighborhood, or predictions that are outside the data set that you have. So just something to keep in mind for the mushroom app, right? So I would definitely not want to do, if I had loads of data on my mushrooms, right? It might work to predict a new mushroom of the same classifier, but if you're trying to predict a completely different mushroom that you've never seen before, right? You should definitely not trust any model on that. Yeah. But okay, so let's do some classification. Some regression machine learning. So for a start, we do something really, really simple. I just generate some data. I use 10 data points on the x-axis, and then I just use a linear relationship. So I just compute 2 times x plus 1. So it's now a linear line with steepness 2. So then we have 10 data points. So now our data, this is now one-dimensional data, just going from 0 to 9 in this case. And then the labels, or the outcomes, are just the numerical values of our function that we've defined up here. But so the trick is now we will forget this function. We don't really have that. We only want to work with the data, and we ask our machine learning now to reconstruct what the relationship was given the data. So now we can plot that data, right? So these are now the data points that we work with. Fairly straightforward. We should probably also add some error here, but I haven't done that in this case. But hopefully, at least if you use a linear regression model, then we should get exactly the line that goes through these data points here again. So one thing that I need to do before I can start using sklearn is remember that sklearn always requires the data to be a 2-dimensional array. But my data sets were just single numbers, so I just now have to wrap every single number here in a list. So now I get a matrix with 10 samples, and I just have one feature for each sample, and that feature is the position on the x-axis. And then here are the labels down there. But otherwise, it's exactly the same as we worked before. And so now I can use a regression model. So now I don't use a classifier model, but now a regression model. And the easiest one is the linear regression model, which just tries to find a linear relationship between the points that we have. So I create a model, and I use the same the same syntax as we had before. I pass in the x, which was the data set, and then y, which is the label. And then once we've done that, we can ask we can call the predict method, of course. But I just asked the model to give me because I know it's a linear regression model, so I can ask it for the coefficient, which is the steepness coefficient, and also for the interception. That's where the line crosses the x-axis. And so then the model tells me, okay, it found the steepness 2 and then the intersection 1. So a line with slope 2 and interception at 1. And if you look at our original model, this is exactly what I've chosen up here. 2 times x plus 1. Okay, so then we've done kind of a very simple regression, and at least it works. So that's a good thing. So now we can do things a bit more complicated. We can generate some random data, which I've done here. So obviously now we don't expect to, well, in this case, it's actually truly random data, so it's difficult to say what a good prediction is. But at least still we can try and fit a line through here. And it works exactly the same way. Right? So you just call linear regression, then fit, and then you can do a bunch of predictions. So here I now created some a numpy array of points where I want to do the prediction on, and then I call the predict function on all these numbers, and then I can plot it again. And so in this case, on this random data, right, you get a prediction that looks like that. But of course, if I run it again, it would be completely different. But so here, maybe a linear prediction isn't so good. So then a nonlinear model might be more suitable. And so one nonlinear model that you can choose is called the random forest regressor. So again, the syntax is exactly the same. First fit and then predict. So and then you would get something like this. Right? So now this is a nonlinear function that tries to go through these data points. And so there's a really important point here, and that was mentioned before, is that you always have to trade off between how many data points you have and how precisely you want to go through match these data points. There's something called overfitting, and that means if you're trying really hard to I mean, this green line here, right? You could have it that you could develop an algorithm that so that the green line goes exactly through every single blue data point that you have in there. So then if you just look at this graph, you would say, well, that's a really good predictor because it matches exactly all the data points that I have. But the problem is then that you're overfitting your algorithm. So imagine if these blue points contain huge amount of errors, right? Then you're actually training your algorithm to also predict or include these errors. Right? So there's a trade-off between how simple you want to have your model and there's a trade-off between how complex or how simple you want to have your model. So this is a very simple model. It's just a linear model, and it's very robust. So even if I had some data points here that were kind of really bad with loads of error, my model wouldn't change very much. I would maybe move this line a little bit upwards here, but that's it, right? So simple models like linear regression are very robust against errors. But then more complex models, here if you introduce a point that was one point that was up here, right? Then more complex model would try and match that point. So it would kind of go crazy up here and try to match that point and then go back and so on. So then the more complex you make a model, the more unrobust it can be. Right? And that problem is known as an overfitting. Okay, any questions? That was it. I don't have anything else. Comments, questions? Then you're done. Thanks. That was awkward.